safety times 10 to the power 6 divided by 28.233. By right, I should put minus sign on both sides. Our factor of safety is equal to 250. Power of 6 divided by 28.233 power of 6. Okay. So our factor of safety is 8.854. Okay. Now, what I want to highlight is this. I'll let you all finish copying. There's a statement that I'm going to make that's really, really important now. Okay. Watch here. Okay, watch here. Is our structure shown on the screen now under uniaxial direction? Uniaxial loading direction, is it? Yes or no? It is not. You have what? You have normal stress, you have bending moment, and you have what? Shearing stress. When we test our material, how do we test our material? How do we test our material? We test just by using what? One direction. And this direction that we test, the shear stress is equal to what? Is equal to 0. Okay? So only at one point on Mohs circle where shear stress is equal to 0, it is at the where? Principal what? Principal stress. And you know that this is constructed using what? 3D Mohs circle, yes or no? So therefore, when we select material over here, or to calculate the factor of safety, right? We also have to use the what? Principal what? Stresses. Are we clear? Do not know this. Designing, manufacturing turbine engine for most work and cannot going to make a profit. Are you clear? Okay, you know exactly what you do. Remember this. However you test your material, you calculate, you somehow have to what? Manipulate the value such that you can use similar conditions relative to the experimental work to the what? To your calculation. Are we clear? We mechanical engineers were really good at this. I don't know why. Remember I told you guys, we take forever to make a pint of beer, yes or no? We keep on drinking and do nothing. Are we clear? Okay, this is what you should know. Any questions so far? Yeah.
Is there a reason we find the XY?
Say it again.
Is there a reason we find the XY and Y plane circles?
Yes. The reason why you want to do that is you want to make sure that your in-plane stresses are your highest. Okay? Good question. Okay? So for this case, right? It happened to be, so if you look at this, so our XZ plane, okay, our XZ plane, this is our what? This is our in plane. The rest are our what? Out of what? Plane. Out of plane. In fact, for this case, if you just draw 2D Mohs circle, you will get the same results. I repeat again, if we just construct 2D Mohs circle, if we just construct a 2D Mohs circle with our what? Our exact case, okay, you will get the same result without drawing the smaller circle. But remember on Friday, what happened? Remember we did this example? You have to go into what? 3D Mohs circle. So the 3D Mohs circle aspect is to check your in-plane has a what? Highest stress state. Okay, our in-plane has the highest stress state. Okay, now, what I've just done
is I've just shown you how to apply 3D Mohs circle. Okay. Now, I hope all of you are convinced that this is important. I'm going to go into the theory on 3D Mohs circle. Okay. And it's not so difficult, not as much difficult at all. Okay. So now, three-D Mohs circle, we have three different conditions. Okay, before we go on 3D Mohs circle, we are going to first look at the element associated with 3D Mohs circle. So if we look at the element, X, Y, and Z, the element will always look like this. So we have our what? Stress X, stress Y, and stress Z. Okay. No shearing what? No shearing stresses are acting on the what? On the element. Okay. If there are shearing stresses, what must we do? We must resolve to its what? Principal plane. I repeat again. In order to get no shearing stress, right? This has to be rotated to be at the principal what? Plane. Okay. So in real life, you can have shearing. So what do? We rotate the element to such a sense that you don't have any what? Shearing. Yeah. So this is at its principal plane. So with reference to the element, okay, we have three conditions. Okay. So we are going to do condition number one. Okay. Condition number one is such that stress X is greater than stress Y. Okay. And stress Z is equal to 0. And stress X and stress Y are both positive. Okay. So that is our condition number one. So now I'm going to label this as my point X. Over here is our point Y, and over here is our point Z. Okay. So now we start sketching Mohs circle for condition number one. So we will have our normal stress, and then we have our shearing stress. And we are aware that over here, this is our stress Z line. Sorry, this is normal stress. This is shearing stress clockwise, anti-clockwise. So the vertical is our stress Z line. Then next comes to our stress Y line. And the last line that I'm going to sketch, this is our stress Z line. X line, sorry. And we are aware that this over here is our point X. This over here is our point Y. This over here is our point Z, because the shearing stress is equal to what? 0. From here, we can construct 3 circles. So this is our first circle. And this circle belongs to who? Anyone? What plane? It belongs to our X what? Our XY plane. Okay. Later on, we go into the in plane and out of plane. The next circle that we can construct, okay, the next circle that we can draw is this circle over here. And this belongs to which one? YZ plane. And the last circle I'm going to sketch is here. Okay. And now this belongs to our what? XZ plane. Okay. So now, if we look at the element, right? If we look at the element, we know that over here, this face over here is our what? XY plane. And the XY plane is our what? Our in plane. Yes or no? It's known as the in plane because it has the biggest what? Surface area. Okay. The next one over here, this is our YZ plane. And our YZ plane is our out of what? Our plane. And finally, we have our what? XZ plane. And our XZ plane is what? Out of what? Plane also. Okay. So now if we were to look into our mole circle now, our XY plane is our what? In plane. Our XZ plane is our out of plane. And finally, our YZ, okay, our YZ is also our what? Out of what? Plane. Right? So why is this important? Right? Whenever any material fails, all material will fail in what? In shear first. Okay, most material or most ductile material brittle and ductile, brittle cannot stand shear, okay, will fail in shear first. Right? So some of you were to ask me, Eugene, is there any evidence of this? Yeah. If you look back into our table, can someone say something about the shear stress and the tensile stress? Which is lower? Shear. So that is why your material will fail in what? In shear first. Brittle material cannot stand shear. They'll fail even quicker. Are we clear? Okay. So from here, it is important to determine the maximum shearing stress. So for this case, what we have now, over here, this is our what? Our tau max, which is equal to our shear XZ plane max. So we can write this down. So we know that shear XZ plane will be equal to stress X plus by stress Z divided by what? Divided by 2. And note that our what? Stress Z is equal to 0. Shear XZ, not plane, sorry, max, is equal to your tau max. And this is equal to your stress X divided by 2. Or stress max divided by what? Okay? Okay, I'll see you guys in an hour's time.